All right, hi, and welcome to, I made this slide just now, but I still wrote 2015, so it takes me obviously more than 10 months to get the dates right. Hi, escape. Wonder if I should start the recording again here. Okay, so, all right, welcome to Computer Graphics. Like the slide says, and I said earlier before I started the recording, we're going to introduce the course a little bit, what we're going to do here. Introduce real-time graphics as an idea, so what that is, how that's different from other types of computer graphics, and why it is that we're going to be looking at real-time graphics. And then actually after this recording ends, I'm going to be looking at OpenGL a little bit, how that works, and kind of what it is. So to begin with, the lectures will not be recorded, not these lectures that I have in the actual classrooms. However, there will be online material, both pre-recorded lectures, which are fairly kind of short lectures that take each part of the material and go through it fairly fast. So you will have recordings of each material, but in the lectures themselves, I'll be here, I'll go through more detailed explanations, I'll be on the whiteboard, and we'll kind of get a discussion going on what's actually happening, whereas the recorded lectures online are kind of a crash course or a very, very fast overview through each material. So you'll have that. There will also be online programming sessions inside libgdx, which is the environment that we're using. I'll be using mainly recordings since last year, where I'm going through these things. So when I'm doing the kind of programming exercises or programming examples in class now, you know, it might look a little bit different from the recordings, but mainly it's kind of the same idea. So there will be online recordings of these programming sessions. There will be online recordings of fast lectures, kind of covering the material, but in a fairly, not superficial, but in a fairly fast way. The lectures here will be more detailed, and I won't use slides. I'll be working in the programming environment, and I'll be working just on the whiteboard with explanations. What we cover in the lectures is kind of how the computer graphics work, what calculations are behind them, what happens on the hardware when the computer kind of graphics programs are running. So we learn the math and we learn the algorithms behind what's happening. Whereas in the programming assignments, we'll be using OpenGL to do that stuff for us in order to make more interesting programs. So we'll be practically learning to, in the practical part, we'll be learning to use OpenGL to make graphics programs. In the theoretical part, we'll be learning what OpenGL does behind the scenes. So we won't necessarily be using everything that we learn kind of in the lectures in the programs themselves. So it's kind of a split course in that way. So in the lectures, there'll be whiteboard explanations on these algorithms, on these calculations, on the vector math behind it, and examples of how we use this in the programming environment. And then we'll simply have math problems and just step-throughs and algorithms and stuff like that. And this is what will, in the end, be on the final exam. Kind of these explanations, these math problems, and these step-through algorithms and such. So the final exam tests whether you understand what OpenGL is doing, how it happens, and how the math works behind it. Assignments test if you can use this to create computer games or animations or nice programs. Please raise your hands if there are any questions on any of this. So the lab classes, most of them will have programming exercises. We'll just get a PDF with a programming exercise. We'll work on that. I'll help you with that. Or you can work on your actual assignments, like the graded assignments in those classes, get help with that. Some of them will have exercise problems instead, where I'll put exercise problems online, and then in the lab class, I'll simply go through the solutions of those. So it'll be a mix of this, but mainly it'll be programming assignments or programming exercises as such, not graded assignments. And we'll just go through those in the lab classes. They're not graded, these assignments or these exercises, but they're built up in a way that if you finish them on time, you'll have built up to where you need to be to do the programming assignments. So you can usually build on top of these lab class exercises in your programming assignments themselves. Whereas if you kind of wait them out until you have an assignment due, you'll end up having a lot more to do just before you get to the place where you can actually start working on your assignment. So they're not graded, but the time you spend on them is time spent on your graded assignments as well. Any questions on this? This is fairly clear. This is one of the questions we get a lot. So this is the grading. The programming assignments are 50%. These will be kind of 5 to 15% each, 4 or 5, depending on how you look at it, assignments. And then there are 10% which are just problem hand-ins, where we have these exercise problems, you hand them in. I grade them, that's a total of 10%. I don't know exactly at this point how many there'll be, probably 3 or 4, but it just depends on at which points and how we feel when we finish each part of the assignment. And the final exam is 40%, but obviously you need to pass that. So yes, so the programming assignments where you use OpenGL are kind of testing a different thing than the final exam. So even though the final exam is only 40%, that's kind of what really tests whether you get the material, whether you understand the entire concept of it. So it's as important, even though it doesn't weigh as much in the final grade. Okay, so the programming assignments, the first one, which you already have and can have started already, is kind of just to get yourselves ready. Make sure that everyone has the programming environment up and running. Make sure that everyone has some graphics elements and objects moving around so that you have some control over the environment. Once you have that, you can basically start working on the first real assignment. Because as soon as you have control over this two-dimensional world that we have now, you can start building on top of that. Making a 2D computer game is then just kind of more of the same. The only thing you need there is kind of the idea of things interacting with each other, collisions and such, but on top of that, it's just more of the same as we're doing in the first lab class. So you can start thinking about your first, or about the second programming assignment right away. So the first one, just to get everyone on the same page, it's due next week. And yeah, that's all I have to say about that. You don't need to worry about details in that. Just make sure it does what it's supposed to do. All the details on how cool it is and stuff like that. It's fun. Definitely, if you want to go all out in the first programming assignment and hand that in to me, I might give you bonus points for that. That's great. I always have fun grading assignments that do that, but you should rather focus kind of on your next assignment. Just make sure the first one does something. The second one, which is the first kind of real programming assignment, will be a two-dimensional computer game. So simple graphics, boxes and circles and such, but a little bit of vector math to move those things around, vector math to kind of have these objects interact with each other, make sure that they collide with each other. But other than that, it'll be an open assignment. You can choose whatever computer game you want. I will have some examples in the assignment description. Fairly common ones are bricks or Arkanoid, or I don't know what name you know that from, where you have a paddle and you have a ball, and the ball bounces around, and whenever it hits a brick, that brick disappears. And your object is to make sure the ball doesn't fall off the bottom of the screen by moving this paddle around. So you have a collision with the paddle where you can control it, so different parts of the paddle will send the ball in different directions. You have collision interaction with the bricks themselves. You have to make sure you calculate correctly which brick the ball hits at each point. That disappears and the ball bounces off the correct side of that brick. You understand where I'm going. These little interactions, collisions, will be kind of the most complex part of this. So bricks is a nice game. You can also go and do something like something similar to Star Control, where you have two spaceships floating around, or asteroids, where you have one spaceship floating around and you're shooting at asteroids, and they float around, and whenever your projectile hits them, they turn into more asteroids and then disappear. Again, vector math used to kind of float your spaceship, make the direction, make sure that it accelerates correctly, and collisions to make sure that when the projectile hits the asteroids, they break, and when your ship hits the asteroids, it breaks, and so on and so forth. And there are many more things you can do. I've had descriptions of kind of a tanks-like game where you have a cannon at the bottom and you kind of move that around and shoot a ball, and this ball then bounces off objects that are in your screen. So these kind of things, simple vector mathematics and simple collisions. Any questions on this assignment? It'll be due in around 3 or 4 weeks from now. It's a fairly quick start on these assignments. After around 2/3 of the course, we'll have assignments 3 and 4, which are kind of the same assignments. It's a 3D maze, but I like to split it into 2 assignments. One of the assignments is kind of building the objects, building the maze, traveling around with your camera. So you need to manipulate the camera, you need to manipulate your perspective, move the camera around and set it up. You need to build the walls that you see, you need to display specific models, and you need to make sure that when you walk into the walls, you don't go through them. So this is kind of the game itself. The second part of it is making sure that your lighting and materials and colors work correctly. And for this, we have to make shaders. So I split it into 2 assignments. One of them is the main game, the game code and the OpenGL code. The other one is the shader code, which is a little bit different in the OpenGL shader language. So that's really the third or the second main assignment, is this maze game. It's not as open as the other one. I expect you to do a specific type of maze game, but it's still always open to interpretation for anyone who's creative. And finally, the third main programming assignment is assignment 5, which is a very open assignment where you simply do whatever 3D game or 3D animation that you want. The only criteria is that you use OpenGL for it, and there are specific things that you need to do. You need to use models, you need to use lighting and colors, and then certain other criteria that you have to choose which ones you use. If you travel along specific types of curves or paths, if you use fog, or if you use transparency, or if you use different materials and textures in your game. So the final one is fairly open. So again, you can, if you want, start thinking about what you want to do in that assignment right away and kind of think about that as the course progresses. But usually you kind of need to go through around 2/3 of the course before you have a feeling for actually what you can accomplish. At this point, I imagine most of you have images in their heads of things that are probably more complex that one will, in the end, manage to do. I don't want to hit that down. Definitely keep those images in your mind and make sure that that's what you're going for. But as the course progresses, you'll kind of get a clearer image of what's possible to do, what's feasible to do, and what things are kind of in the realm of more complex computer graphics than we're going to be looking at now. So questions on the assignments? No?
Sounds, will we go over how to use sounds in the course?
It's not specifically part of the material, but I can help you with that in lab classes. And once we start using the 3D graphics in libgdx, I'm pretty sure you'll find it very simple to use the sound banks of libgdx as well. So definitely use sounds if you want to. It's not part of what I grade specifically. Everything you add kind of has a bonus effect. So I grade with main criteria and bonuses. So I like creativity. I like things that I didn't ask for specifically. So yes, sounds, a lot of people will use sounds, but it's not as such part of the course. Yes. Mainly the functionality, but I look over the code to make sure there are specific things in the code are done in the way that I kind of have dictated as such. So there are certain things I want to keep separated in your code. And once the programs get more complex, I expect you to kind of make classes that do specific things. A class for an object, and it has a function that can update its position, and it has another function that can update this model in the correct place, so on and so forth. So doing it in this way, yes, that affects your grade, rather than ending up with this one big main file with your code all over the place. But it's mainly the functionality that I grade. but I check the code to make sure that you're actually writing that functionality in OpenGL or in ways that we've discussed. So I don't grade the code as such, but I make sure that certain things are there and done in the correct way. Yes. Any other questions on this? Okay, so right now we're kind of talking in the end of the course. We're talking about these end products and what they're going to look like, and we're imagining these computer games that we're going to make. But it's nice to kind of start a little bit at the beginning and just look at what computer graphics are. So we have kind of different types of computer graphics. We have what's called ray tracing, which is a very common way of rendering like animated feature films and anything that's pre-animated. And then we have simple things like vector screens and specific type screens for math graphs and such. And then we have what's called pipeline graphics, which is what we're going to be looking at. And at the same time, we have these different end products that different things apply to. So we have math graphs and high detail static images, which can be done in many ways. Then we have these pre-rendered animations, which in general use ray tracing, where you have films like Disney feature films, where everything is built up in the beginning, everything is designed in the beginning, then it's rendered, and it can take months, even years in some cases in old movies, to render the entire film. Just the calculations of rendering each frame can take many minutes or hours for each frame, and then you load this on huge server banks. So months in big server banks just rendering these images, just doing the calculations. So once we're thinking about real-time graphics in computer games, it kind of becomes clear that this is not the method that we're going to be using there. Because what real-time graphics are is simply graphics that are rendered at the same time as they're being displayed. So real-time graphics and pipeline graphics is kind of the buzzwords that we're going to be looking at. We're doing real-time graphics because we're doing computer games. Our computer will be rendering our animation as we're looking at it, which is necessary for computer games because we can't pre-render a computer game. As soon as you hit a button, you affect what is supposed to happen in the game, and then it has to be rendered in a new way because of what you did. So real-time graphics is what we're going to be looking at, and pipeline graphics is kind of the calculation method that is used most commonly for real-time graphics. OpenGL is a standard for pipeline graphic rendering, and that's what we're going to be using in our assignments. So if we look in a little bit more detail at real-time graphics, just for computer graphic animations or any animation or film, we have frames. So an animation is simply just a sequence of frames that are run at a specific speed. In classic films, it was decided that 24 frames per second was some kind of ideal amount of frames. So 24 images each second would be enough for you to feel entirely immersed, and you wouldn't see any difference if it was made faster. In the last decade or two, I think all computer game enthusiasts have kind of decided that this 24 frames per second isn't some ideal thing. It's just kind of the least amount of frames that you need, so it's actually not just flickery. So kind of modern expectations for computer games are more like 50 frames per second at least, which means that we need to display on our screen a new frame, a new full image 50 times each second, which means we have 20 milliseconds image that we're going to draw, because 20 milliseconds later, we're going to need a new image. And a lot of competition computer games are set up in ways that you can get 100 frames per second or more, which means that you have 10 milliseconds to render the entire scene that you're looking at. So it feels like a short amount of time to render if you just think about the last computer game you played and what each image is like. If you would just stop in that computer game and look at what's happening. In many cases, there are tens of other characters in the view at the same time. You have backgrounds, you have vegetation, you have houses, you have very detailed models. And all of this is drawn in its entirety in somewhere between 10 and 20 milliseconds of computation time. Because as soon as you hit a button and you turn around a little bit, it's an entirely new image that you're rendering, which means it has to be rendered all over again at the same time as you hit the button. So obviously these are massive calculations that need to happen in a very short amount of time. And I don't know how many of you saw the question on Piazza that came in just either this morning or yesterday, that I answered on, when you first start doing this, you really feel like, why am I redrawing all of these boxes into my scene every single time that I do a new frame? And when you just have these boxes moving from side to side, it feels like, can I just color another box on top of it, which is in the same color as my background, and then just draw the new box here? Everything else will stay in place. And in original two-dimensional computer games, this is exactly what was done. When you have side-scrolling computer games, ID Software and John Carmack were the first to do it on the PC, but it had been done by Nintendo earlier on side-scrolling computer games for the NES, where you'd actually just take the image and you'd move what you already have on the screen a little bit to the side, and then you just render a single column of pixels or a few columns of pixels, depending on the speed that you were moving. And when your character was moving around, you'd simply memorize what should be behind him in the scene, and you'd re-render that and then just re-render the character. So as much of the background as you have could still be there and more or less unchanged. What they did at ID Software was actually not take all the pixels and move them, but instead move where they were reading from the buffer. Does this make sense? So they'd say, okay, this frame, we're going to start reading from the buffer here, and we're going to go in a circular motion here. So nothing had to be changed except where the character is in the image. And then you can get side scrolling without more or less ever redrawing anything except a single column of pixels. Yes, most of those games, yes, those are kind of sprite animations or sprite blitting, which the technique is called. So each ad is simply a two-dimensional image, which is of a fixed size in pixels. And when you add it to the screen, you simply go through each pixel and you draw that color on top of the screen. You wouldn't have any transparency there because that would be very expensive at that time, but you would maybe have a color key where you'd say this color here is transparent. So if you get this color in the sprite that you're doing, you don't draw anything. Any other color goes over, which means that even though the sprite is a box, then the image that is being drawn can be a character or whatever, and the background can be seen through. Anyway, this is not what we're going to be covering now, but it's an interesting idea because you feel that these optimizations are possible. But as soon as you think about a 3D image, if you imagine that you just move your camera, you just rotate your camera by a few degrees, then you don't really move everything to the side. The perspective in everything changes. If anyone has just done perspective drawing courses or anything like that, you understand that as soon as you move a little bit to the side, your image doesn't just move a little to the side. It's not like holding a frame and moving it to the sides. You're actually changing the perspective of everything, which means that you can't do this. You can't just take a 3D image and move it to the side and add a little to the side. So in the end, in true three-dimensional real-time graphics, especially with perspective projections, which is what all computer games have, you pretty much can't reuse anything in your frame. As soon as you do a little motion, everything will be different, which means that in the end, so this is the long answer to what I answered on Piazza. The answer to that is what every computer game that you see does in the end, whether it seems well optimized or not, is they simply clear the screen and redraw the entire scene from scratch. Again, there are certain things that can be reused. You can kind of bake textures and lighting into things beforehand, and then when you draw the model, you can keep that on hand. But the three-dimensional image itself, the three-dimensional rendering, the OpenGL functionality, you just need to simply clear that away and redraw the entire thing. So in the third part of the current assignment that you have, where you're supposed to click with the mouse and a new box is added every time, you need to have some data structure that holds those boxes, and then every time you draw the frame, you need to redraw all those boxes. Because if you do it the other way around, you just add it to the frame. As soon as I move the screen around or resize it or something, it'll clear, and all those things will disappear except the ones you add after that. So part of this assignment is not, strictly speaking, OpenGL or graphics, but keeping track of your objects, keeping track of your computer game model. And that's something that we're going to need to look at as well, whether it's computer games or animations that we're doing. Part of computer graphics is always keeping track of your objects, of your model, of your scene, in order to be able to draw it onto the screen when the time comes. So other questions here? So I think I've covered everything that's on this slide through those questions, right? We're building each frame from scratch because, yeah, and we need this speed because each frame is rendered just right before it's displayed. And the double buffering versus single buffering thing, we'll look at that better later. But the idea is in double buffering, we're drawing into one frame while the screen is reading from another. So the screen is kind of refreshing itself on one frame while we're drawing in another. When we're finished drawing this frame, we simply tell the screen, you refresh from here now. And then we start drawing in the other. That means we never get flickering where you can see the image being drawn into the screen. If you use single buffering, if you have a fairly slow program, it doesn't even need to be that slow, you'll start seeing your boxes appear as you go through frames. So that always looks, that's a flickering of a much worse sort than the flickering that you got using double buffering. And besides, the double buffering flickering can be fixed simply by redrawing the scene entirely every time. Okay. So what the graphics pipeline does, or what any computer graphics program needs to do in order to make an image, it needs to position some kind of camera, some kind of point of view. This is where we're looking from. It's pointed in this direction because this is what we're looking at. So that's set up. We set the perspective. That is, how wide is this camera? Is this like a very wide 180-degree fisheye lens, or is this like a zoom, or like looking through a scope? So we set up this perspective, which decides exactly how things are rendered to the screen. We need to take thousands of vertices. So if you imagine a model, each model has hundreds or thousands of points along its surface. And we need to position these. We need to fill in the area between them. We need to set a color to these. We need to have the lights, which are in our scene, affect each of these vertices. And then we need to shade the areas between them. So at this point, maybe this doesn't make sense to all of you, but we'll get into this. But you can imagine that this is a lot of calculations, calculating the color first for each vertex in these models, and then for each pixel between them in order to shade this entire thing so we get a solid object and not just this kind of grid of points. And to do these things and position these objects, we need to manipulate the coordinate frame or the coordinate system that we're working into for each point, calculate the light, and after we've done this, we need to set up some viewport on the screen, say this is where we want this to be on the screen. Either it's full screen and it takes the entire screen, or it's part of your window. And then we need to take the image that is rendered out of the 3D and move that onto the 2D screen that we have. So all of this needs to be done, and we have hundreds of thousands or even millions of these points or vertices in the scene, in each frame, in a complicated computer game. And all of this needs to be done 50 to 100 times per second. So obviously, a massive amount of work, a massive amount of calculations. But the graphics pipeline has these operations that are done in a specific order, use very particular calculations and algorithms, try to kind of weed out things that won't be shown in the end as early on in the pipeline as they possibly can, calculate colors in as few places as is needed, and then kind of gradient them over areas, these kind of things. So we're going to learn about how these algorithms, how these calculations work, in which order they're done, in order to basically throughput these huge amounts of vertices in a short amount of time and still get fairly convincing or very convincing graphics out of it, even if we don't have the time to render everything in minutes or hours like we have in actual animated cartoons. So that's basically the kind of idea, what we're going to do or what we're going to learn how the pipeline does. And this is kind of an overview of these different algorithms and calculations. So the first thing that we're going to be looking at in the course is actually just a little bit of a recap on vector graphics or vector mathematics. So maybe a lot of you have taken linear algebra. Those who haven't taken a course in linear algebra, there is one of these kind of fast online lectures that I've put in on vector math, so you can look at that and kind of go through that and recap a little bit there. There's a section on vector math in the online book that we're using. And then you can go online or ask me and we can get up to date on that. But we're going to take a little bit of a crash course in vector math and then look at specific ways that we use vector math in computer graphics, like finding angles between vectors, reflecting vectors off of other vectors, these kind of things that we can use in the end when we do lighting calculations, use when we do collisions in our computer games. After that, we're going to be looking at different matrix transformations. Again, I hope most of you have a base in linear algebra. If not, we'll have material that can recap that. So the matrix transformations that we'll be looking at will be geared specifically towards computer graphics. So it's not as broad as what you learn in linear algebra, but in some cases it's also different and done in a different way. So we'll be looking at two-dimensional and then mainly three-dimensional matrix transformations that are used. Here we have this model matrix, which is used to kind of position all the models and the objects that we have in order to be able to draw a single set of vertices, but in different places. We want to draw the same model in different places. We don't want to have to make the vertices all over again. So instead we say we have this manipulating matrix that we run each of them through, and we change that between renders. Okay, so model matrix, view matrix is the position and the orientation of the camera. We have the projection matrix, which is the perspective. That is, how is the camera? What's the lens like? And also, what are the depth calculations going to be like? Then we have depth calculations. We have lighting calculations. After those, we'll probably be around the middle point of the course. Somewhere after 5 or 6 weeks, we'll have looked at lighting calculations, and we'll see clipping, window to viewport transformations, and finally rasterization, which includes shading and texturing and transparency and depth tests and such, where we're actually taking these images out of this three-dimensional continuous world and putting them into the discrete world of pixels that's on our screen. So all of this will be explained in steps. This is one of those materials where I'd feel best if I could just teach you all of this at the same time, and then it will all make sense to you. Some of it won't make sense until after we learn other parts of it, if you get where I'm going. But you know, around the time when we're looking at the rasterization, everything kind of starts to click for everybody. And so while you'll probably understand the calculations and the algorithms, you know, each of them in their own bubble, in the end, our objective of the course is to understand how they interact with each other, why we're using all of them, and how each of them is a necessary part of this pipeline, and how we get from the vertices that we send in as programmers to the actual image that appears on the screen. So questions on this? I think it's a perfect time now to take a short break. So if there are no questions here, we'll resume with a little bit of an OpenGL overview after a 5-minute break. Or is it 10 minutes? Okay.